Now let's consider an application of the derivative, which is about velocities or speed. So here's what you have. Suppose you have a road. Okay, this is one straight road, and you are moving along this road. So suppose you try to move to the right. You start at some point, okay, and you have a certain speed, and then at another time you will be at another location, right? So suppose this is 0, and you have what we call the position function. So we say this is position, we use s, and it's a function of the time, ft. So what that means is at a certain time, so t is the time, maybe after 1 second, right? You start at 0. This is when you have t equals 0. After say 1 second, you're 3 feet from the starting point. So at this is 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, and so on. So when t equals 1, you are here. So you're here when t equals 1. Okay. This number line represent the position. So this is just this road position. At t equals 1, you are at position 3, and at t equals 2, maybe you're here. Okay, and t equals 3, you are at position 6. Okay, so your position depends on the time. So we call that a position function. Now you can see that in the first 1 second, okay, between time 0 to time 1, you move 3 feet. Within the second, you move from 3 to 5, you move 2 feet. All right, and within the third second, you move only 1 foot. So you can see that your speed is getting lower and lower, right? And we can calculate this speed from the position and the time. So here's how we do the velocity. So we know that, right? The velocity or speed is equal to the change in position. We call that displacement over time, right? So if you can cover 3 feet in 1 second, the velocity is 3 feet per second, right? If you can cover 10 feet in 2 seconds, then your speed will be 10 over 2. That will be 5 feet per second. So this is how we define velocity. It's a change in position over the time to do that. But this is only an average velocity. This is the velocity during the first second or during the second and so on. So it's only an average number. And you also have what we call a instantaneous velocity. Okay, this is the velocity at any time point. So this is actually the speed you read from the speedometer, right? When you drive a car, you can see at this moment you are doing 55, right? Maybe 10 seconds later, your speed increased to 63 or something like that, right? So that's the instantaneous velocity. And instantaneous velocity is defined to be a limit of the average velocity. Okay, so the average velocity here, you can define that to be the change in position on the top. So that will be your position, okay, between time. So let's say we start at time A, and we consider, so the starting time is A, the ending time is A plus H, okay? So the time interval is H. And then you have the position at A and A plus H. And the difference of these two will give you the change in position. So you have A plus FA plus H minus FA. Right? So this is like that. You have position and you have time at t equals A. You are at FA. And after H, so the ending time is A plus H. And your position is FA plus H, And your average velocity will be how far you cover divided by the time it takes to cover that. That will be H. So the denominator will be H. Right? So that's average velocity. And for instantaneous velocity, it's the limit of that. And H goes to 0. In other words, you want to look at two time points which are very close. One is A, one is A plus H, but these two are very close, so H is very small. And then you look at how much distance you can cover during this time H. Okay, so that limit is defined to be the instantaneous velocity. So this is just a very special case of the derivative, right? This is how we define the derivative of the function f, and we call that VA, instantaneous velocity at time point A. Okay, so this is the velocity. And we can try some examples on that. It's just a special case of the derivative. So once you know the position function, ft, and you know the time, you can always get the velocities. So let's try this example. Suppose you have a very tall building like that. Okay, this is a building. And you drop a ball from the top of the building. Okay, you just release that. And we know the ball will fall to the ground, right? The ball will move downward, and the speed will become higher and higher, right? Because of the gravity. So suppose this is position 0, right? And we're looking at the axis which goes downwards, right? This is 0, and this is like 1 foot below 0. This is 2, this is 3, and so on. Right? So we know the gravity will pull down the ball to the ground, and there's a rule for that, right? So the position, or f of t, which is how far this ball is after t. Okay, after say 1 second, where is the ball? After 3 seconds, where is the ball? Okay, so this is the position, and physics rule tells us this is 4.9 times t squared, and that's in meters. So t is in second, which means if you drop the ball after 1 second, the ball will be 4.9 meters from the starting point. So this is 4.9. That's when t equals 1. So t equals 1, the ball is right here. Then after 2 seconds, the ball, so say for example, f1 is 4.9 times 1, times 1 squared, that's 4.9 meters. After 2 seconds, that will be 4.9 times 2 squared, that will be 4.9 times 4, that's about 20 meters below the starting point. And you can do any position. Okay, so that's a position function. Now, how fast is the ball? How fast is the ball moving at any time t? So we have this instantaneous velocity, okay, at any point. So this is instantaneous velocity at time a. Okay, a could be any second, 1, 2, 3, and so on. So this is the limit, right? It's right here. This is the limit a plus h, fa plus h minus fa over h. And we know this f function is 4.9 times t squared. So you can just plug in a plus h, that would be 4.9 times a plus h squared. So this is the position of the ball after a plus h seconds, and minus 4.9 times a squared. Okay, this is the position of the ball after a seconds, right? And that difference here is the change in position, and the ball covers that distance in h seconds. Okay, so this is simply a plug-in for this instantaneous velocity. And you can simplify that. And remember, h goes to 0 because we want to know the instantaneous velocity. So we only look at a very short time period, okay? And that gives us this average velocity, but within a very short time period. And that's how we define this instantaneous velocity. So you can take the product, right? It's going to be a squared plus 2ah plus h squared minus 4.9 a squared over h. Right, so these are very simple algebra. You just do 4.9 a squared plus 9.8 ah plus 4.9 h squared minus 4.9 a squared. Over h, right? And you can cancel this with that. And you can also see that you have h on the bottom, and the remaining terms on the top, they both have h. So h is here, and you have h squared. So you can cancel h from the top and the bottom, and you get 9.8a plus 4.9 h, right? You can take out this h and divide it by h if you want, and h cancels. So at the end of the day, you have limit h goes to 0, 9.8a plus 4.9h. And remember, h goes to 0, right? Because we want to know the instantaneous velocity. So the time interval is very short. H goes to 0. Then you just get 9.8a. Right, because this term will go like 0. So the instantaneous velocity at time a is equal to 9.8 times a for whatever a number. Okay, so this is the instantaneous velocity. Now you can see that if you want to do any time, say 1 second after you drop the ball, or 20 seconds after you drop the ball, so the instantaneous velocity after 5 seconds after dropping the ball, right? So that's a equals 5. So the v is equal to 9.8 times 5. That's 49 seconds per 49 meter per second. This is the velocity. So you can see that that's very fast, right? So that's why it's very dangerous if you anything falls from a very tall building. So be careful about that, right? So this is velocity. Now let me show you another example, all right? And this example is not about velocity. It's a very general example. So the function, right? I give you a function. I want you to calculate the derivative of the function at some point. So the function is 1 over square root x. All right. So this is a function, and I want to calculate the derivative of the function, or the slope of the curve. Okay, how steep the curve is at a equals say 1. All right. So you have a function here, and the curve of the function will come with a derivative, a slope, and you want to know the slope at x equals 1. All right, so let's try that. The derivative of the function at 1, okay, it's a limit. You have 2 definitions, right? So you have to this, and remember, a is equal to 1, so it's x plus 1 minus fx, and x plus 1 minus x. Sorry. It's x minus. Yeah, it's right. Okay, so a equals 1. All right, so let me write down the original formula. It's the limit x goes to a, fx minus fa over x minus a. So it should be like this. Let me fix that. It's sorry, fx minus f1 over x minus 1, like that. All right. So we know the function is 1 over square root of x. So f1 is 1 over square root of 1, x minus 1, like that. Now you have to simplify this, right? Try to do some cancellations and hopefully get some nice numbers. And all right, how do we do that? You have this quotient on the top, all right? And we don't really like quotient, so let's try to get rid of this square root of x and square root of 1. So yeah, you can just do square root of 1 is 1. So what you have on the top is simply this. Okay, now how do we get rid of the square root of x? Let's multiply by square root of x everywhere, both on the top and also on the bottom. So this is what do we do? All right, if you multiply by something, you have to do that for both numerator and denominator, and we are doing the same thing right here. So we can still keep this equation. Now the top, you can see that the first term will be 1 over root x times root x, so that will give you 1. The second term is square root of x. Like that. Okay. Now, another trick is we want to get rid of this 1 minus root x. So one common trick is let's multiply by 1 plus root x. All right, you multiply by the same thing at the top and also the bottom. So you still have this equation. Now, the numerator, you can see that will be y minus x. So the product of these two give you y minus x. And on the bottom, you have x minus 1, root x, 1 plus root x. All right, now you can cancel. You can see that you have y minus x, you have x minus 1. These two can cancel, but you have this extra negative 1. So you will have negative 1, and on the bottom you have two terms, root x, y minus root x. Now it should be easier to see what's going on here, right? When x goes to 1, the top is negative 1. You don't do anything with negative 1. It's just a negative 1. It's a pure number. But for the denominator, you can do the limit, because this is a continuous function. Now, if x goes to 1, what do you have here? This will go to square root of 1. That's still 1. And the second term will be 1 plus square root of 1, right? That's 2. So what you have is negative 1 on the top and 2 on the bottom. Okay, so the derivative of this function, 1 over square root of x, has a derivative negative a half at x equal to 1. So the derivative is negative, right? This is negative. And this is the slope. Derivative is the slope of the tangent line. So that means, because it's negative, the curve is moving downward. It's kind of, move like that. Okay. So that's another example for derivative.